everyone. Now I would like to share with you the last topic of Laplace transform, which is applications of Laplace transform. Do you know why engineers use Laplace transform? Actually, in real industry, engineers deal with systems that change with time, such as motors, robots, vehicles, and power systems. So most real engineering systems are described by the differential equations, which are difficult to solve directly. So especially when the system becomes very complex. So what the Laplace transform does is very powerful. So it converts the problems from the time domain into S domain. Then differentiate the equations become the differential equations become very simple algebra equations. So this allowed the engineer to design the controllers such as PID controller, predict how fast a system responds, and check the overshoot, setting time, and steady state behavior. This is why Laplace transform is widely used in automations and robotics, power electronics, and electrical systems, electric vehicles, especially the motor control, communication systems such as analog filters. So in practice, engineer does not solve everything by hand. So they use tools like MATLAB, Simulink, or PSCAD, which are all based on the Laplace transform model. Previous topic, you have learned about the region of convergence, or ROC. But why is matter? In fact, Laplace transform alone is not enough. So we must know whether the system is safe or unstable. So this is why the ROC or region of convergence become very important. So ROC tells the engineers whether the system is stable or not stable, whether it's causal, or whether it can be implemented in the real hardware. So there is a very important rules in industry, such as if the system poles are in the left half plane, so the system is stable. So if the poles move to the right half plane, the system become unstable. So why does this matter? Because unstable EV motor controller can cause the vibration and sudden accelerations. So it's unsafe accelerations. And also, an unstable power converter can damage the equipment. And lastly, if in aerospace, instability can lead to the catastrophic failure. So in this topic, you will learn about characteristic of the LTI system in terms of causality, stability, and LCCDE. Also learn about the application of circuit and system function algebra. This slide telling you what is rational number. Rational number where A divided by B, in which A and B are integers, and B cannot be equal to 0. And a decimal point is a rational when it terminates or ends, like for example, 1.5 equivalent to 3 over 2, or 1 over 8, or 3 over 4. All of them are integers. Or it can repeat with a pattern. For example, 4 over 3. 4 over 3 equivalent to 1.333, although 1.333, but is equivalent to 4 over 3, so it's still considered as a rational number. Or if the number with 0.16666 equivalent to 1 over 6, and 1 and 6 both are the integers, so they are considered a rational number. But what is not non-rational number? They are like pi. Okay, there are exponents or square root of 8, okay, and etc. Laplace transform can be used in the analysis and characterization of LTI system using convolution properties. So as you know, convolution properties is a yt equal to xt convoluted with ht. This is in time domain. If in s domain, there will be ys equal to xs hs. It's a multiplications. If the ROC of the HS includes the imaginary axis, this means we can safely evaluate the system as at the S equal to j omega. So when we substitute S equal to j omega into HS, the result is the frequency response of the LTI system. So in simple terms, this tells us that how the system responds to sinusoidal input at different frequencies. So the function itself is called system function, or more commonly called transfer functions. So it represents the input-output relations of the system in the S domain. So there are so many important properties of the LTI system can be closely associated with the characteristic of the system function in the S-plane, such as the stability, frequency response, transient behavior, and physically reliability. All these can be directly determined by the location of the poles and the zeros of the HS in the S-plane. A causal LTI system means the system does not respond before the input is applied. So mathematically, this means that the impulse response satisfies the ht equal to 0 for t less than 0. For a causal system, the ROC of the system functions lie in the right half of the S-plane. So however, we must be careful that the ROC of the rightmost pole does not guarantee that the system is causal, but it only can guarantee that the impulse response is right-sided. Okay, so however, if the HS is rational, causality can be determined by checking to see if the ROC is right half plane. So therefore, for a system with a rational system function, causality of the system is equivalent to the ROC being the right half plane to the right of the rightmost pole. What is anti-causality? An anti-causal system responds before the input is applied. So for the anti-causal system, the impulse response satisfies the ht equals 0 for t more than 0. So this means that the impulse response is left-sided, or the system only has a response before t equals 0. So in the S domain, this means that the ROC of HS is lying at the left half plane. So if the ROC is the left half plane, it only tells us the ht is the left-sided and does not guarantee the system is anti-causal. So in the practical terms, if HS is rational, the ROC to the right of the rightmost pole, this means that the system is anti-causal. Here is a comparison between causality and anti-causality, where causality, the ht equals 0 for t less than 0, and the HS is rational, and ROC is right of the rightmost pole. Whereas for the anti-causality, ht equals 0 for t more than 0. Okay, for more than 0. Then H is rational, the ROC of the HS is to the left of the leftmost pole. So bear in mind that the ht is referred to the impulse response and HS is referred to the system function, or we so-called the transfer function. Let's look at the example. Consider a system with impulse response ht equal to exponent power negative t ut. So this is the unit step function at t equals 0. Then determine the causality of the system. So the answer is the ht here equal to 0 for t less than 0, because unit step is start only at t equals 0. So for those less than 0, the ht equals 0. So this is the answer for the t less than 0, you get ht equals 0. So therefore, it's a causal. And hs is equal to 1 over s plus 1. It's a rational number. And the ROC of this HS is to the right of the rightmost pole, because 1 over s plus 1. So s is more than negative 1.